Welcome back. We gotta get rock and rolling on some strain transformation. So we want to define plane strain, develop the strain transformation equations, and then apply those equations to solve some engineering problems. So lots to do, so let's get started. So just like stress, we can define strain on a particular element by 6 components. So we have our normal strain. We refer to that as epsilon, and that would be in the x, y, and z directions. And then we have our shear strain. That's defined by the variable gamma, gamma xy, gamma yz, gamma xz. So if we can define these 6 components of strain, we'll know the state of strain on a particular object. But just like we did with plane stress, we're going to consider examples of plane strain. So what happens? What's the condition for plane strain? Well, all of the strains need to be in just one plane, like the xy plane. So if epsilon z is considered to be 0, and gamma yz and gamma xz are also 0, we have the state of plane strain. I want to warn you, and you can go ahead and box this in, highlight it in red, whatever you need to do. Plane stress and plane strain are not the same thing. So, due to the Poisson effect, sigma x and sigma y will cause the material to dilate or contract in the z direction. What does that mean? I want you to think back to our Jello cube, right? When we push down on our Jello cube in the y direction, we get expansion in the x direction, but we also get expansion in the z direction. Okay, so even though this is an example of plane stress, because I only have a stress in one direction, in the y direction, it is not plane strain because I have some sort of epsilon y, epsilon x, epsilon z due to that Poisson effect. So, just want to caution you, plane stress and plane strain, not the same thing. Where do we see examples of plane strain then? I'd say they're typically involve states of loading or states of strain on large or long objects. What does this mean? So think of a long or a large object, and we consider the strain on that. So one example comes to my mind is a railroad track. On a railroad track, on the rail, you might have very high loads from the train cars pushing on the rail in one direction. But the rail in the length of the direction really isn't expanding. So even though, Poisson's effect would say it would be expanding, because the railroad is so long, right? It's miles and miles and miles long. When the train is at one spot pushing down, the rail is really not extending in the z direction. And so therefore it would only be, compressing in the y direction and then maybe extending outwards, bulging a little bit, but it really wouldn't be extending along the length of the railroad. So that's one example of plane strain. Kind of similarly with this, we could consider like gas pipes, or any kind of pressurized pipes. That are very long, because inside the pipe they have a lot of pressure. They're going to be expanding outwards in this direction, but they really can't get longer along the length. So think about like the gas line running to your house. Again, it's miles and miles long, so it can't really extend in the z direction. Another good example in civil engineering here we have are our dams. So in the dam, right, you have the dam. The dam is super long. It's got a compression from the water, but it really can't extend along the curvature of the dam because it's just so big. It's really kind of not expanding. Another good example are soils. So when you load the earth itself, the earth is just huge. And so really, as you press down on the dirt, it really can't just expand infinitely into the earth. And so that's another case where we often come across plane strain. So hopefully you have those ideas as to what plane strain looks like. And I'd say although plane stress and plane strain don't happen simultaneously, these in-plane strain relationships that we get, the in-plane strain relationships, will still be able to apply to plane stress cases as well if we need to solve for the strains that are occurring. But we do have to make sure we account for Poisson's effect if we're working with plane stress. All right, so I'm going to go through, we're going to derive the plane strain equation. So just like we did stress transformation, we're going to do strain transformation. So hopefully you're excited for that. I'll talk to you in a bit. To perform a strain transformation, we're going to do a displacement analysis. So I want to take my original block there shaded in gray, and I want to apply epsilon x, epsilon y, and gamma xy to this block. And I've applied all of these two normal strains and the shear strain in what we have as our positive direction. I've also anchored the block at the origin, so all the displacements are anchored at the origin and drawn relative to that location. The black line, this parallelogram, now represents the displaced shape of the element after I apply a positive strain in the x direction, a positive normal strain in the y direction, and a positive shear strain gamma xy. We are interested in solving for epsilon x prime, where x prime is some angle theta from my original x-axis. To work through the geometry, I want to give the original block length in the x direction the dimension dx. The rotated block will have a distance dx prime, and this dx prime basically refers back to dx but rotated at an angle theta. Now, I need to solve for this delta x prime total, is what I've labeled it in here. So this is the amount of stretch that my block has stretched in the x prime direction. So this is the total distance it has stretched in the x prime direction due to epsilon x, epsilon y, and gamma xy. In order to solve for epsilon x prime, I will take delta x prime total and divide it by dx prime. So this is just delta L over L0, just like our regular strain equation. I also need to include dy, so I'll go ahead and draw that in, and then I want to come up with the relationships dx equals dx prime cosine theta and dy equals dx prime sine theta. To start solving for delta x prime total, I want to look at just the effect to delta x prime total due to epsilon x. So on this block, I'm only going to apply a strain, a normal strain, in the x direction. This will cause my block to stretch as shown. Now, if my original length of my block is dx, the amount that it moves in the x direction is going to be delta x. Now, for my analysis, I'm not interested in delta x, I'm interested in delta x prime. So I'm interested in this distance, the amount that is changed in the x prime direction. And this distance is just the amount it changes in the x prime direction due to epsilon x. So I'm sort of only considering one of the three strains that I need to do to get delta x prime total. If I want to solve for delta x is just the strain times dx. So this is just strain times the original length, epsilon x dx, will give me the amount delta x that I've stretched in the x direction. With the angle, and recognizing that delta x is my hypotenuse in this case, then the component in the x prime direction due to epsilon x is going to be delta x cosine theta. And then substituting for delta x, we have that this is epsilon x dx cosine theta. I can repeat the same process solving for delta x prime when I have a strain epsilon y applied to the block and a strain gamma xy applied to the block. So I go through the same process and come up with the components of change in the x prime direction. If I did that, I would find that delta x prime due to epsilon y is going to equal epsilon y dy sine theta, and delta x prime due to the shear strain gamma xy equals gamma xy dy cosine theta. Now my total displacement, delta x prime total, is going to be the sum of these x prime displacements. So delta x prime total equals delta x prime due to epsilon x plus delta x prime due to epsilon y plus delta x prime due to gamma xy. And so now I just substitute my values above. So this equals epsilon x dx cosine theta plus epsilon y dy sine theta plus gamma xy dy cosine theta. I'm now ready to solve for epsilon x prime. Epsilon x prime equals delta x prime total divided by dx prime. So now I'm going to substitute the values above for delta x prime total, but for dx and dy, I want to substitute the geometry I had on the previous page, namely that dx equals dx prime cosine theta, and dy equals dx prime sine theta. So if I do this and I substitute dx, dy, and the value for delta x prime total, do a little bit of algebra, you'll see that I have dx primes in the numerator and a dx prime in the denominator. So those will cancel out. And now I can write my expression for epsilon x prime. Epsilon x prime will equal epsilon x cosine squared theta plus epsilon y sine squared theta plus gamma xy sine theta cosine theta. I think this equation's worthy of being boxed, so let's go ahead and box that as our strain transformation equation, epsilon x prime. We can repeat this problem for epsilon y prime, or we can just use epsilon x prime and substitute theta equals theta plus 90 degrees to get the epsilon y prime equation. And we can also do it for gamma x prime y prime, and we would get the following results. Applying our trigonometric identities and shuffling things around, we would see that we can develop these strain transformation equations for epsilon x prime, epsilon y prime, and gamma x prime y prime over 2. We can solve for the principal strains. We can solve for the max in-plane shear strain. And then, like we did with plane stress, we could also develop a Mohr circle for plane strain if we wanted to, plotting epsilon versus gamma over 2. Thank you. I hope you found that super entertaining to get the strain transformation equations. So we got our epsilon x prime equation, and so I think this is like our set list for the day, right? We have all the tracks that are awesome. And So we also have our epsilon y prime equation, gamma x prime y prime, principal strains, the angle to the principal strains, the max shear strain, and then also the average strain, average normal strain that corresponds to the max shear strain. So just like stress transformation, we can develop all the same equations for strain transformation. We note that they're very similar, except we replace sigma with epsilon for strain, but we replace tau with gamma over 2. So just make sure if you're trying to use the stress transformation equation, you can replace sigma with epsilon. Then for everywhere you see tau, you have to replace it with gamma over 2. All right, so that's just kind of the set list. Now we're going to use these equations to solve an example problem. In this example, we're going to do a very basic strain transformation. And so your engineering firm has been asked to conduct an in-service analysis on whatever you think is going to make for in-plane strain. I'm going to say maybe a dam or something. So I like to have a little picture here. Let me see if I can get something in here. We got rock. Got my water behind there. Water down here. Maybe rock all the way down here. Draw whatever picture makes you happy. If you want to draw a railroad, because that was a good example. Soils, go ahead. Whatever the case is, as long as you have in-plane strain, this problem will work. So, again, I've drawn a dam here. All right. So, you attach strain gauges to measure strain in the field, and you come up with these values for epsilon x, epsilon y, and gamma xy. You want to determine the equivalent in-plane strains on an element that's rotated 20 degrees counterclockwise from the original position. Then we want to sketch the deformed shape of that element. So, how do we solve this? We just apply our strain transformation equations. So, part A, remember we said epsilon x prime. We developed this equation. You can refer back to our set list if you need to. It's got epsilon x plus epsilon y over 2 plus epsilon x minus epsilon y over 2 cosine 2 theta plus gamma xy over 2 sine 2 theta. So all we need to do is to substitute for epsilon x, epsilon y, and gamma xy, and we get the answer. Again, making sure that we substitute with the negative sign. So I'll go ahead and work this one out with you. We got epsilon x is 270. I'm just going to put everything in here in a bracket. So we got 270 plus minus 350 over 2 plus 270 minus a minus 350 over 2 cosine of 2 times theta. Theta here is 20 degrees. So it's going to be cosine 40. Or we could write 2 times 20 if you want to have that down. Cosine of 2 times 20 degrees. Plus gamma xy is a positive 420 over 2 times sine of 2 times 20 degrees. All the brackets are then multiplied by 10 to the negative 6. So just kind of makes the calculation a little bit easier by not having this 10 to the negative 6 in the whole thing. So we go through 270 minus 350 gives us a negative 80 over 2. So this should give us negative 40. Plus 270 minus a minus 350 gives us 620. 620 divided by 2 is positive 310. Cosine 40 plus 420 divided by 2 is 210. Sine 40. All times 10 to the minus 6. Then we can go through and do this math. You should solve that epsilon x prime equals 332.459 times 10 to the minus 6. All right, so hopefully that's pretty simple. Just plugging it into the strain transformation equation, making sure we do our algebra. We got to do it for epsilon y prime and gamma x prime y prime. So again, I'll just point you over here to our set list. We want to use the epsilon y prime equation, and then we want to use the gamma x prime y prime equation, making sure you don't forget that there's this extra 2 over here. So after you do everything on the right-hand side, make sure you multiply by 2 to solve these. So go ahead and give that a try. And after you do that, you should get to the following answers. Epsilon y prime is a negative 412.459. Times 10 to the minus 6. And gamma x prime y prime is equal to negative 76.790. Times 10 to the minus 6. All of these are units of strain, so there are no units here. And we have our answers. All right, so that completes part A. So hopefully you can get to these answers, give your calculator skills a try. And we're going to solve part B next, where we want to sketch the deformed shape of the element due to these strains. Sketching the element is one of the harder things to visualize once we have these transformed strains. So I've gone ahead and drawn my block. The black dashed line indicates the original block, and we want to know what happened on an angle when we rotated it counterclockwise, an angle of 20 degrees. So I've gone ahead and drawn my x prime and y prime axis as well as the element, the original shape of the element. Now, we have epsilon x prime. It is a positive number, so positive strain means that it's stretched. So if I anchor this point at my origin, I'm going to anchor this point, so this point is not going to move. Then if I had a positive strain in the x prime direction, this block would extend in the x prime direction. So I would have, this point would move in the x prime direction, this point would also move in the x prime direction. Now I want to consider what's happening in the y prime direction. In the y prime direction, we have negative number, negative strain. That means compression. So in the y prime direction, this block is compressing. So that's going to push this point down. And remember, we move down a bit. This point's going to shift down a bit as well. Finally, we have gamma x prime y prime. And this one is a negative number. So remember, our positive shear strain would be positive x prime, positive y prime. But the negative number indicates that my shear strain on my block is going this direction and this direction. So this is negative shear strain. And so I then want to skew my block in this direction. So this block is going to get skewed downward. So maybe to some new point like here. This one's also shifting down. This one is skewing back this direction. So maybe we get more of a skew back and a little bit up. So I have a rotation like that. Something like that. that. I think I like this point out here a little bit better. It's skewed a little bit more. We come back to the start position. So this is what the deformed shape of our particular element would look like, due to a positive epsilon x prime, so it shifted out a little bit, a negative epsilon y prime. You can see it shifted down a bit from this original green dashed line, and we also had a skew that caused skewing like this and like this, and so we have this final shape. So hopefully you're able to follow through with that. If not, practice makes perfect. All right, we'll see you soon. In honor of example 1, I wrote this little song for you, and it goes something like this. Take me down to the paradise city where our examples are fast and the equations are easy. Oh, won't you